So as we saw in that video, mathematicians have honed in or did hone in on this way to mathematically represent this idea of covering half of the distance every single time. So here you can see it as a graph, how they graphed it of one step, they're at half of the distance, whether this is kilometers, as this one says, or maybe it's miles, or maybe it's meters, or maybe it's just one whatever unit. And so after one step, you've gone halfway. The second step, you've gone half of the way, which would be a fourth, right? So then this is, you can see 0.75, so 3/4 of the way there. And then another half of that, right? They've cut that distance in half. You can even see the distance between here and here. That distance is now half of that, and half of that, and half of that, and half of that. And you can see that this is one half, right? They went a distance of one half. And then they went a distance of a fourth more, half of that, right? And then half of jumping a fourth would then be jumping an eighth, which is here. And then half of that would be jumping a 16th, and then a 32nd, and so on. This can be represented, this is a series, by the way. If we remember all the way back to sequences and series, we can see that this is a series. This is why we learn about sequences and series. And it's a series that's represented by repeated multiplication, multiplying by a half. Repeated multiplication is what type of series or sequence? Remember that repeated addition is an arithmetic sequence. You added 2 every single time. You added 5 every single time. Here, since we're multiplying by a number every single time, it's a geometric sequence, which is then turned into a series. How you represent this is 1/2 to the n. So when mathematicians figured this out and they were saying, well, the idea is that it goes on forever and ever and ever, so you never actually reach your goal. And it was because sometimes mathematicians get too stuck in the concept of something as opposed to the reality of something. And so what they ended up doing is they proved that, oh, well, that ultimately will just bring you to your goal, which means that you traveled that one distance. They needed to, when they came up with this mathematical process, they needed to give it a name, which, like, you've seen this very often in mathematics where there's these weird, crazy, kind of scary names. In trigonometry, we see it, right? This idea of sine, but also like logs, right? Logs are this big, weird, scary thing when really it's just the idea of undoing an exponent. But we're talking about this really complicated process, and so we have to give it a name. And this is what we call a limit. And so we give it a name of a limit, of this idea of infinitely approaching something, which ultimately just means that you are that. And we represent it with this notation. You'll notice that here it's written like this. I always do a curly M, a curly L, just because I think writing an L like this looks like 1, and in mathematics, that's no bueno to have something look like 1. So I just write it like this with the curly L, so that's why. So we say the limit as x approaches infinity. So how we talk about limits is we say, okay, what is the limit as x approaches infinity? And so you can look at this x-axis and say, okay, well, as x goes closer and closer and closer to infinity, in other words, going to the right, your y value is getting closer and closer and closer, like an asymptote, right? It gets closer and infinitely approaches this number 1. So the wording of this is what is happening to y, or what is going on with y, when x approaches this value. Now, there's a little stipulation on here when we start calculating for limits, is that it's not just as x approaches that, it's as x approaches this value, infinity in this case, but you'll see down here like x approaches 1. We're going to say as this value, when x approaches this value from the left-hand side and the right-hand side. We'll look at in future lessons why the left-hand side and the right-hand side have to agree, and in instances where the limit might not exist, would be when the behaviors are different. We'll talk about it now. The instance where the behaviors are different are something that looks like this for your non-continuous functions, which means that a continuous function is where if you put your pencil, kind of like your continuous graphs of continuous variables, if you put your pencil on the page and trace this graph, you would never have to lift up your pencil to talk about it. This is not continuous. It's a rational function. It's not continuous because I would have to lift up my pencil and put it somewhere else. If there was a gap in your function, it wouldn't be continuous, and so there wouldn't be a limit. So as approaching this guy right here from the left-hand side and the right-hand side, my behaviors of y are different. This one goes down, 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 down. This one goes up, 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 up. So that's why the left-hand side and the right-hand side have to agree. If they don't, the limit doesn't exist. I'm pretty sure IB doesn't ask you to know when the limit doesn't exist, but just to put that on your mind of, because we're going to talk about in this lesson about the left and the right-hand side, that's why, is that it has to agree or else the limit doesn't exist. Here, approaching it from the right-hand side, in other words, coming from the other side of infinity, it doesn't really work with the idea of infinity, but it's still approaching this. We're still having the same situation going on. Okay, let's put this to practice. I would like for you to grab your graphing calculator. Pause for you to go get it, even though we use it every time. I want you to grab out your graphing calculator. I want you to go to the graph. I want you to click on the white space and delete whatever else you got going on there. Notice that that's what we're going to do later. Wow. Okay. And what we're going to do is we're going to graph this equation. What this is asking is, what is the limit as x approaches 1? And how we think about that is, what happens to y as x approaches 1? So what we're going to do is we're going to graph this function because we're saying the limit of this guy right here. So I'm going to do x plus 1 y basta. And this is what it looks like. It's a line with an a y-intercept of 1 and a slope of 1. So this is what it looks like. And if we were to put our brightness down so you can see that better, maybe it's as dim as it goes. I'm going to graph trace this. So if you hit menu and then you go to trace and then you want to do graph trace, and I want to see what is happening as x approaches 1. I could just type 1 in and press enter and say, oh, here's the point. The point is 1, 2. I just realized that my answer key is wrong. So here is the point that happens there. And it isn't always so nice. It won't always exist at that point. We'll talk about that in a second, but this is about as simple as we get with limits. And so what we have to think about for a second is, as x is approaching 1 from the left-hand side, so we're looking at the left-hand side and we're saying, hey, as x is getting bigger, right, as we're coming in here from the left-hand side, what is y approaching? Well, we're getting closer to 2. Or from the right-hand side, as x is getting negative, what is happening to y? Well, it's approaching 2 as well. So we're saying, hey, from both of these sides, they kind of like an arrow point in and say, hey, we're going to 2. You could also make a table of values. This is a new set of steps, so pay attention. If you click menu and you go to table, you can always turn your graph into a split screen table. And it'll show you that behavior. Hey, as x is approaching 1 from the negative side, from the left-hand side, it's going to 2. And same from the right-hand side, as it's getting negative, it's going towards 2. So how we write that is, hey, the limit as x approaches 1, if you ever see this little negative guy up here, it's saying 1 from the left-hand side, from the more negative side. From the left-hand side, right, this side right here, x, you're less than, you're negative of that 1. And so then that's why it has a little negative up there. Versus, then we'll talk about limit as x approaches 1 from the right-hand side. So little bits of notation that you probably haven't seen before, and that's just what it means. From the left-hand side, from the right-hand side, there we go. So the limit as x approaches 1 from the left-hand side of x plus 1 equals 2. And it's the same with the right-hand side. Since they agree, we can say, hey, okay, well then the limit as x approaches 1 of x plus 1 is 2. So it's pretty nice that way. It's not always going to be that nice. Let's see a situation where it might be a little bit less nice.